unstable nuclei will become more stable. Imagine a boulder on the crest of a hill. The boulder has a lot of energy because it's high up on a hill. It can lose some of this energy and become more stable by rolling down the hill. This process will give out a different kind of energy equal to the difference in the potential energy of the boulder at the top of the hill and the potential energy of the boulder at the bottom of the hill. You already know all this if you've listened to my podcast about gravity and energy. The point of this podcast is to discuss the geography of the hill the rock is sitting on and the geometry of the boulder itself. A rock on a hill has a chance of falling down, just as a nucleus in an atom has a chance of breaking apart. Falling down for a rock makes it more stable. Breaking apart for a nucleus does the same thing, given certain conditions of the initial nucleus. The rock falling releases potential energy. A nucleus falling apart releases a different kind of potential energy. The closer a rock is to the centre of a gravitational field it sits in, the less potential energy it has. The smaller the nucleus of an atom, the lower the potential energy it has to further break apart. However, unlike a rock falling down a hill, which has an almost infinite number of paths it could take to the lower energy level, a nucleus has far fewer. The route that a nucleus will take to decay depends on two things: how large the nucleus that is going to decay is, and how far from stability that nucleus is. On an NZ graph, as discussed in previous podcast, you can plot a graph of the average stability of nuclei. This can be called a stability line, although it does not mean that a nucleus on this line is stable. It just means that nuclei on this line will have the longest half-lives. The N for the graph means neutron number, and the Z means proton number. And for this situation, N is on the y-axis and Z is on the x-axis. 4 mechanisms for nuclear decay will be discussed here. These are alpha decay, beta minus decay, beta plus decay, and electron capture. Alpha decay contains the most energy, and so allows for the biggest changes within an unstable nucleus. Beta decay contains the next most energies and are twinned in that they have exactly opposite paths to become more stable. Electron capture is similar to beta decay, but in reverse. Very large nuclei away from the stability line need to lose a lot of energy, so undergo alpha decay. This will lower their potential energy and bring them closer to the stability line. Even after losing this large amount of energy, the new nucleus will probably still need to lose energy, but at a lower amount. This is where beta decay comes in. Whether it's plus or minus depends on the composition of the nucleus. If the nucleus is below the stability line, when the nucleus will lose energy through beta plus decay. If it is above the line, it will decay via beta minus decay. If the new nucleus still needs to lose energy, it can lose it through gamma decay, which is dealt with in another podcast. Electron capture is slightly strange in this context. Sometimes a nucleus has too many protons but not enough energy to emit a positron. It can undergo beta plus decay, but is still so unstable that it won't just lose energy through a gamma ray. Instead, a proton captures an electron from the inside of the atom and converts it to a neutron. In our analogy of the rock on the hill, we would say that the rock has changed shape and fallen a little bit down the potential hill. The nucleus is slightly more massive, but the new nucleus has far fewer forces pulling it apart. On an NZ graph, the nucleus would move from below the stability line up, slightly closer to it.